Hi everyone. So in today's video, we're going to be talking about a new derivative rule called the product rule that will let us take the derivative of a product, so multiplication of two functions. So today's topic is going to be the last thing that will be covered on the midterm that's coming up on Friday, so just heads up on that. Also, just sort of to kind of set the tone for what the rest of the week is going to be like. So, when we first started talking about derivatives, we learned this limit definition that allows you to take the derivative by, computing a limit, basically. And from here on forward, we're really not going to be using that definition so much. We might use it to prove some of these new rules, but we're, for the most part, going to just be learning all these different rules that allow us to take derivatives of different types of functions. So I just want to kind of make you aware of that it's probably going to start to feel like pretty different from what we were doing like last week, but you do still need to remember how to find the limit definition or use the limit definition. It's just that we're not going to be using it all of the time anymore. Okay, so this is section 3.2 in the book. So basically, I want to kind of tell you what the product rule is, and we'll do some examples, and then at the end I will prove the product rule, because I just think the proof is kind of a cool proof. Okay, so in what situation would you use the product rule? So let's say that you wanted to find the derivative of the following function. Suppose you wanted to find the derivative of the following function. H of x is equal to x squared times e to the x. So we don't know how to take the derivative of a function like this yet, right? We know how to take the derivative of x squared, that uses the power rule. And then we know that the derivative of e to the x is just e to the x, but we don't know how to take the derivative of the product of two functions that can't kind of be simplified together. So we don't, maybe let me write that down. So we have not yet learned how to find the derivative of a product. So product means multiplication, right? Of two functions. So I'm going to start by telling you what does not work, and then I'll kind of try to convince you that it's not the way it works, and then we'll learn the actual rule that does work. So the rule that is not true, it is not true that, so like let's say that you wanted to take the derivative of this function above, the h of x function. It is not true that h prime of x is just equal to, okay, let's take the derivative of x squared, that's 2x. Let's take the derivative of e to the x, that's e to the x. Unfortunately, it just does not work that way. So in general, it is not true that if you're trying to take the derivative of the product of two functions, so in like the example we did above, f of x would be x squared and g of x would be e to the x. So if you're trying to take the derivative of two functions, it does not work to just take the derivative of each of the functions individually and multiply them. It does work to add, right? If our function was x squared plus e to the x, that actually works, but it just doesn't work with multiplication. So let's see another example. I want to really show you why this doesn't work. So, how can we know for sure this doesn't work? So let's actually just try a function that we do know the derivative of, and then we can kind of find a way to write it as a product, and then try using this fake product rule, and we'll see that it doesn't work. So we know, for example, let's say that we're looking at the function x to the fifth. We know just based on the power rule that the derivative of this is equal to 5x to the fourth, right? So power rule just says take down that exponent, subtract 1 from the exponent, and so this is the correct derivative. But let's say that instead we decided to rewrite x to the fifth as x squared times x cubed. Right, that's the same function. We haven't done anything wrong yet. That function is completely equivalent to the original function. So let's say that now you decided to use this incorrect product rule. So if you tried to take the derivative of this using this thing up here, you would get 2x times 3x squared. And that's equal to 6x cubed, which is a completely different function from what we know is the correct function, right? So this just does not agree with what we know is the correct function. Maybe even just to give like a more convincing example, like what if our original function was, I don't know, let's just say a constant, so like 4 times x. So we know that the derivative of a constant times x, well, it's just going to be the slope of that line. So it's just going to be 4. So we know for sure from previous classes, we know that that is our derivative. But if you tried to use this, this other rule, so if we tried to say, okay, this is 4 times x, let's use this incorrect product rule. And let me switch colors for my signaling of the incorrectness. So if you tried to say, okay, we'll do the derivative of 4, the derivative of 4 is 0, and then the derivative of x is 1, and you get 0, well, that's completely different from what we know the derivative is. We know the derivative is 4. So hopefully I've convinced you that that is not how you take these derivatives, and you will not do that in the future. So now let me tell you what the actual product rule is. So the real product rule, so I'm just trying to scroll down here. So the product rule. So if you're trying to take the derivative of a product of two functions, let me throw some color in here to make things interesting. So let's say you have two functions, and we're going to call them f of x and g of x. So the way that you take that derivative is you start by taking the derivative of one of your functions, and it's actually not going to matter, but let's just say the first one. And then you just multiply it with the second function without taking the derivative. And then in the second part, you switch. So now you take the derivative of the second function and you multiply it with just the original function, first function, without taking the derivative. So let me put a box around this because this is super duper important. This will come up quite a bit. Okay, so let's see how this would actually apply to the example that we started out with. So the example that we did at the beginning, or that the question I posed at the beginning was, if our function is x squared times e to the x, how could we take the derivative of that? And so now we have this rule that tells us how to take the derivative. So our x squared would be our f of x, right? And e to the x would be our g of x. And so what the product rule tells us is that our derivative should be equal to the derivative of x squared, so that's 2x, times just e to the x, like without taking the derivative. Although with e to the x, when you take the derivative, it doesn't change. But just to be clear, when we first write it down, we're just writing it down just as the original function itself. So if it was a function besides e to the x, then that would make a difference. And then the second part, well, now we're going to take the derivative of the second function. So e to the x, again, in this case, it's the same thing as whether you take the derivative or not. And then we just multiply it with our original first function. And so maybe a nicer way to write this would be, I would probably write this as 2x e to the x plus x squared e to the x. That's it. So we're going to do a few more examples. There's actually not that many examples we can do so far. So later this week, starting on like Wednesday, we'll learn the derivatives of some trigonometric functions, so like sine and cosine, and then we'll really be able to practice a lot more with using the product rule as well as the quotient rule, which is what we'll learn tomorrow. But right now, the problem is we just don't have that many functions to work with. We only really have polynomials and e to the x. So we'll do a couple more examples, but starts to get a little bit boring after a while because it's just not too much that you can do. Okay, so let's say that we have the function h of x is equal to 5x e to the x plus 3 over x squared plus 1. So this is going to be an example of a function where we're going to kind of use different rules for different parts. So notice that this part here is a product. So we're going to have to use the product rule because we're like blending together an x part with e to the x part. This part here, we're going to be able to just use the power rule. We won't need to use any kind of product rule. And then the last part here, this is just a constant. So, I mean, we know how to take the derivative of a constant. Okay, so when you take the product, or when you use the product rule for something like 5x e to the x, you kind of have a choice. You can either set the 5 aside and then multiply it in with the derivative of x times e to the x at the end, or you can just kind of pair that 5 with whichever part you want. So the way that I tend to prefer to do it is I usually will just pair it with one of the two parts. So what I mean by that is I would call, in this case, f of x, the first function in our product rule, I would just make that be 5 times x. And then I'll make g of x be just e to the x. But if you wanted to, what you could do instead is you could do like 5 times, x e to the x, and just focus on taking the derivative of this inside part using the product rule and then multiply in the 5 at the end. That would work as well. You'll get the exact same answer either way. Okay, so let's go for it. Let's try to find our derivative here. So for the product rule part, we're going to apply the product rule again. So we're going to start by taking the derivative of 5x. So the derivative of 5x is just 5. And then we're going to take the derivative, then we're just going to like leave e to the x as it is and multiply with that. And then next we're going to take the derivative of e to the x, which again is just e to the x. And then we multiply that with 5x, so our original function. Okay, so now let's take the derivative of the next two parts, right? Because we do know that when you're taking a derivative of a function where you're just adding up different things, you can just kind of focus on each part individually and just add up those derivatives at the end. So we might want to rewrite this as, so this power rule part, let's rewrite this as 3x to the negative 2, right? That would be an equivalent way of writing 3 over x squared. And so once we have that, then we can just take the derivative using the power rule. So we'll have 3 times negative 2 x to the negative 3. Right, so just applying the power rule for that part. And then lastly, we have the constant. And when you take the derivative of a constant, it's just 0. So now we can clean this up a little bit. So we have 5 e to the x plus, and I tend to like to write, if I have e to the x, I tend to like to write it at the end before or after like any kind of powers of x, but it doesn't really matter. You could totally leave it written as above. If you wanted to, you could factor out the 5 if you like how that looks better. It doesn't really matter. And then here we have minus 6 x to the negative 3. If you wanted to, you could rewrite that as 6 over x cubed. And that's it. That's our derivative. Okay, so I want to now look, so this example and the previous example, these were two examples where you actually have to use the product rule. I want to do a couple of examples now where you don't have to use the product rule, but just to kind of like show you that, that it still kind of works, if that makes sense. So maybe I'll even write that down so that if you're looking at this later, I'll write it on a separate page. So if you're looking at this later, you won't think that I'm telling you to use the product rule on these. So you do not need to use the product rule. So I just wanted to go back to that first example that we did. So, or maybe it's the second example. So let's say that we have the function h of x is equal to x cubed times x squared. So you definitely do not need to use the product rule on this, right? You can just say, okay, x to the fifth, and we know that the derivative is 5x to the fourth. So let's just write that down because we already know that. We already know that the derivative should be 5x to the fourth. But let's say that you decided to use the product rule. Let's just kind of like confirm that you would actually get the same thing. So if you wanted to use the product rule, you know, we'd have our first function. I don't know if I'm using the same exact color sequence as I did before, but that's okay. So let's say you wanted to use the product rule. So this would be the this first method is power rule. This is now product rule. So if you wanted to try to use the product rule, you would get for the x cubed part, you would get 3x squared. So take the derivative of x cubed. Then you would just multiply that with the second function, so just with x squared. And then the second part of the derivative, we would take the derivative of g of x, so that's going to give you 2x. And then we're going to multiply that with the original f of x, and so that's going to be x cubed. So let's simplify this. So you would get, in the first part, that would be 3x to the fourth. And then the second part would be 2x to the fourth. And then, surprise, surprise, that comes out to give you 5x to the fourth. So I just wanted to kind of come full circle and say, you know, we saw how like using that fake wrong power or product rule did not work for this. If you, for some reason, really wanted to use the product rule, you could. It would work here. It's consistent with what we would expect. I also want to show you the other example that we did, which was h of x is equal to 4 times x. So again, this is one where you do not need to use the product rule. So I want to be really clear because a lot of people end up, I think, starting to just use the product rule in places where they don't really need to. Anytime you have a constant times a function, you don't need to use the product rule. You can just kind of take that constant aside and take the derivative of the other part. Or in this case, because it's just a linear function, you could also just think of it as the slope of the linear function. But the kind of more generalizable way of doing this would just be saying, okay, the derivative of this is going to be 4 times the derivative of x, which is 1. So I'm just left with 4. If for some reason you really wanted to use the product rule, you could say, okay, I'm going to take the derivative of the first function. So the derivative of 4 would be 0, right? And then we would multiply that 0 with the second function. So that would be with x. And then we can take the derivative of the second function, so g prime of x, that would be 1, and multiply that with the original f of x, which is just x. And lo and behold, we get, I'm sorry, I did something wrong. I just wrote, yeah, sorry about that. I wrote, so when we took, let me walk back for a second. So the second part is the derivative of g of x, right? It's g prime of x times your original function f of x. And the original function f of x is just 4. So we're just doing 0 times x plus 1 times 4. And so now I can say, lo and behold, we get 4, which is what we already knew the derivative was. So basically it checks out. It works the way it should. And like I said, we'll do more examples later in the week with using the product rule on slightly more complicated examples. But yeah, main thing I just want you to know is, how to use it. And then also, just like we saw in this other example, you can use it in conjunction with other rules, right? So you can have a function where only part of it is a product, and then the other parts you might use other rules. And so as long as your function is put together with addition or subtraction, you can do that. You can kind of break it apart into pieces and take the derivative of each piece using the rule that you need for that piece. Okay, so now I want to get into the proof of this. So this is going to be, I think that this is actually a pretty cool proof, but it's definitely a little bit tricky and technical. And I just want to make it really clear that you don't need to understand the proof in order to use the product rule. So if you followed the beginning part of this video and you know how to use the product rule based on the examples we did, you're fine. I mean, you don't even really have to watch this next part. I personally think it's interesting, so I would give it a shot and listen to it and watch it. But if you're not really understanding it fully, that's totally okay. It's not going to be something that you're going to be held responsible for. It's more just because, like I've mentioned a few times, I really don't like to just kind of tell you a rule without giving you some kind of reasoning for why that rule is. So just in case you haven't taken math classes that have a lot of proofs in them, so what is a proof? A proof is basically when you start with things that you know are true and you kind of go through steps to demonstrate that something else is true. So what we're going to do is we're going to start with some kind of framework that we already have been using for derivatives, and then we're actually going to pull in some geometry, that's kind of the cool part of this proof. And then we're going to basically use what we know about limits to show that the product rule works, that the product rule that I told you at the beginning is actually true. So it's like we're starting with something we know is true, and we're kind of taking legitimate math steps to come to a conclusion of the product rule being what I told you it is. So that's generally what proofs are like. Okay, so what are we trying to show? And I think oftentimes when you're doing a proof or when you're reading a proof, you start by saying, like, what is it that we're trying to show? So the goal of this proof is to show that the derivative of a product of two functions is equal to the derivative of the first function times the second function plus the derivative of the second function times the first function, because that's what I told you the product rule is. So I want to convince you that that really is the case. So how are we going to do this? We're going to go back to the limit definition of the derivative. And so we're going to start by writing down basically how would you write down the derivative of a product of two functions using the limit definition. So how would we write this down? Well, we know that in general, the derivative of a function is supposed to be the limit as h approaches 0 of, if it was just f of x, it would be f of x plus h minus f of x over h. But because it's a product of two functions, it's actually going to be f of x plus h times g of x plus h minus f of x times g of x over, oops, I don't know why it won't. Oh no. That's behind the scenes. You're not supposed to see that. Okay, there we go. Over h. So why is it like this? Well, basically, anytime you have a product of two functions, if you're trying to like plug something into a product of two functions, you just plug it into each function individually and multiply them together. And that's really all that's going on here, is that, f times g of x plus h is the same thing as f of x plus h times g of x plus h. Okay, so what I want to do is we're going to draw a diagram, and then we're going to basically see how the thing that's written here can be interpreted in terms of areas in the diagram that we're about to draw. So we're going to draw a rectangle. Let me just go ahead and draw it. And I want you to imagine that this rectangle is changing its size as time goes on. So why am I saying that? Well, basically because we want the we want like one dimension of this rectangle to be f of x and another dimension of this rectangle to be g of x. So let's think of our input variable x in this case as being time. So what does it mean to say that the length of this is f of x and the width of this is g of x? It basically means that the length and the width are both varying as functions of time. So for the sake of simplicity, maybe let's picture that f of x and g of x are both functions that are getting bigger as time goes on. So let's imagine that as time goes on, so as x gets bigger and bigger, these two different dimensions of the rectangle are both going to get bigger and bigger. They might not get bigger at the same rate, right? They're two different functions, but they're both just kind of increasing. So if you think about it, what are we trying to actually find here? If we're looking for the derivative of the product, we're actually trying to find the rate of change of the area of this rectangle, right? Like f prime of x would be the rate of change of the length, and g prime of x would be the rate of change of the width. And what we're looking for is the derivative of their product, and their product would be the area. And so we're looking for the rate of change of the area of this rectangle. That part's actually not really going to come up so much in the proof, but I think it just kind of helps connect, like, why on earth would we be drawing a rectangle in this problem? It's because we're really talking about the rate of change of an area, or at least you could think of it that way. A rate of change of area because it's the product of two functions and not just one function itself. Okay, so as we said, let's imagine that as time is going on, so as x increases, suppose that f of x and g of x are both increasing. So let's imagine that just a tiny bit of time has passed, and we're going to call that extra amount of time h. So what's going to happen after an additional h time units? Well, because we said that this thing is growing, it's going to get bigger. So I'm just going to take this rectangle and basically just make it a little bit bigger. So I'm going to add a little bit in this direction, and that's going to be the horizontal amount that this thing has grown. So this is going to be, instead of being just f of x, so f of x is the length of this kind of shorter side. And maybe let me actually, I didn't want to get too crazy with colors because I'm going to use some other colors later, but I think this might be a little clearer with colors. So the original width of this, or length, I guess I was calling it, of this rectangle is f of x. This longer length is going to be f of x plus h. So why is that? It's because, again, this thing is growing as time goes on. And so if you add just a little bit more time to x, so x is the amount of time, right? If you add a little bit more time, well, the rectangle is going to be longer. And then similarly, and it might not be the exact same amount bigger, but after an extra h time units, so, whatever, imagine it's like 1 second or something like that. Well, what am I calling? I guess now I lost track of which one I'm calling length and which one I'm calling width, but it doesn't really matter. This will also get bigger, right? So I'm using this purple color to represent the dimensions when it has grown that additional amount. Okay, so maybe let me try to kind of summarize what we just did there, and I'll use this purple to kind of link it with what we wrote above. So after h additional time units, f of x plus h and g of x plus h are the new dimensions. Okay, so this may seem completely unrelated to what we were doing above, but actually, if we start to look, and I want to just move this up a tiny bit and I'm not sure. Let's see if I can. This might be one of those things I shouldn't try to do on let me skip, I'll do that later. It's just bugging me how it's a little close to that. So looking at what we have in this limit, notice that like you see a lot of the same stuff showing up, right? We have an f of x plus h, we have a g of x plus h, we have an f of x, we have a g of x, and that's the same stuff that we have down here. So what I want you to notice is, let's say that we wanted to look at the area of this original rectangle, the smaller one in black. So the area of the smaller rectangle is, well, how do you find the area of a rectangle? You do base times height, right? So it's f of x times g of x. And then the area of the larger rectangle, so I'll do this to represent now the larger rectangle. So the area of the larger rectangle is now the bigger dimensions, right? F of x plus h times g of x plus h. Okay, so let's now look back up at our limit and see what we can interpret in this numerator in terms of areas. So the first part of this limit, so maybe let me write down first the limit as h approaches 0. The first part of this limit is f of x plus h times g of x plus h. And we just said that that is the area of the purple, the bigger rectangle. So this is like not super technical math stuff, but I'm just going to, instead of writing that expression, I'm just going to put that rectangle there to represent the area. And then the f of x times g of x part, well, that's the area of the smaller rectangle. So right now you might look at this and say, this is not getting us any closer. Now it just looks like nonsense. There's nothing to evaluate in this limit. And you're right, but we're going to get to a point where actually we're about to kind of do a trick that will let us rewrite this using different different algebra that we'll be able to simplify in an easier way. Okay, so what do you get if we look at this picture here and you take the big purple rectangle and you subtract out the original rectangle? Well, you're left with this thing, right? Like this is kind of the difference. And maybe an even better way of writing that, or a different way, let's just say, of expressing that would be, well, we could break it into two different pieces. And I shouldn't have highlighted all this in one color because I kind of want two different colors. So this is one piece of the leftover, right? And then the other piece of the leftover is this. Right? So if we look at what do you get when you take the big purple rectangle and you subtract out the smaller black rectangle, you're left with this kind of upside down L shape. And this upside down L shape is made out of two pieces, the one that I just shaded in green and the one that I just shaded in like magenta. So I'm going to add that to our confusing shape limit up here. Okay, so now we're going to have, instead of taking the limit of these kind of subtracted areas, we're now going to focus on adding up these two other rectangles. Okay, so let's go down below here now. And I probably should have laid this out a little bit better, but that's okay. So we're going to kind of do what we like. So what was our general approach? We started with something that was written in terms of, function notation. We then retranslated that into rectangles. We translated those rectangles into other rectangles. Now we're going to translate it back into function notation. So if we look at let's start with the, let me think which one's easier. Let's just start with the green one. I think it's a harder one, but let's do it first. Okay, so let's say we're trying to find the area of that green shaded vertical rectangle. So what is the height of that rectangle? the height of it is g of x, right? Just looking at our picture here, the height is like this height, and that's represented by g of x. Now, what is the width? Well, to find the width, we need to subtract the longer purple length. So the width is like this length here, right? And how can we get that? We can get that by taking the longer length in purple and subtracting out the shorter length in black, right? When I say purple, I mean like the darker purple. So if we do f of x plus h minus f of x, that's going to be the like short side of this. So maybe I'll even write that in here. So this shorter side is f of x plus h minus f of x. I know there's a lot of symbols going on here, but I hope that you can just be convinced just by looking at like the geometry of the picture. If you take a longer length and subtract the shorter one, you're going to be left over with f of x plus h minus f of x. You cannot, by the way, simplify that to f of h. If you just think about it, that's not really how functions work. In general, functions don't work so that you can just kind of combine them in that way. So we're going to leave it as f of x plus h minus f of x. Okay, now let's write down the area of this magenta one. Okay, so what's the area here? Well, in this case, the longer side is f of x plus h, right? Because it's like the whole kind of length of this rectangle. And then so that's the long side. And then we're going to do the exact same trick to find the short side. So in this case, the short side here is going to be g of x plus h minus g of x. Okay, so why do we do that? Well, now we can take that stuff and put it back into our limit. So remember what we were left with was the limit as h approaches 0 of the area of the green rectangle plus the area of the magenta rectangle over h. So I'm just going to rewrite that, but now instead of writing in our rectangles, we'll actually write some algebra stuff. So I'm going to put in, and that is really crooked. So let's put in g of x times f of x plus h. I know this looks really crazy and complicated right now, but we're almost done, don't worry. So that was the vertical rectangle, and then we are adding in the horizontal one, and the horizontal one is f of x plus h times g of x plus h minus g of x. Okay. So the next step is we know that when you have limits, you can split them up with addition, right? Like if you have the limit of two things being added together, you can take the limit of each part separately. And so basically, because we have two things, the expression written in green and the one written in magenta, they're both over h, we can split it into two fractions and kind of use that to split it into two limits. So we have g of x times f of x plus h minus f of x over h plus the limit as h approaches 0 of f of x plus h times g of x plus h minus g of x. Okay, so why do we split it into two limits? Well, basically, if you think about what we're trying to show, our eventual goal is to show that when you take the derivative of a product of two things, you get an expression that looks like this, right? This is our end goal. And maybe I'll even highlight that in a different color so that when we get it at the end, we can be like, yay, it matches. So we're trying to show that the derivative can be split up into these two different things that are added up. So it kind of makes sense that we're getting two different limits. So basically what will happen is each of these limits will turn into those two different pieces. Okay, so other thing that we can do with limits is you can split them up using multiplication. So we can change this into the limit as h approaches 0 of g of x times the limit as h approaches 0 of f of x plus h minus f of x over h. And we can change this one to the limit as h approaches 0 of f of x plus h times the limit as h approaches 0 of g of x plus h minus g of x over h. So does anything look familiar here? Well, we know that this thing right here that I'm circling, that's f prime of x, right? That is the limit definition of f prime of x. And same thing here, this is the limit definition of g prime of x. So let's go through and simplify all of this. So the limit as h approaches 0 of g of x, well, there's no h in g of x, so we don't have to do anything. We can just say, okay, that's g of x. And then the limit as h approaches 0 of f of x plus h minus f of x over h, like we just said, we know that that's f prime of x. And then the limit as h approaches 0 of f of x plus h, well, typically when we're doing the limit as h approaches 0, we have some like issues that we have to simplify, stuff like that. But if it's just f of x plus h, you can just plug in h equaling 0 because there's nothing that becomes undefined in that case. So that just becomes f of x. And then as we just said, that second part is g prime of x. And so it's written in a slightly different order. So maybe I'll just reorder this so that it looks more like what we had before. So f prime of x times g of x plus g prime of x times f of x. But this is exactly what we said at the beginning was the product rule, right? So this, what we came up with here, matches with what we came up with up there. So that's it for today. And thank you if you watched all the way to the end for bearing with me. I know this was pretty complicated, but I think it's pretty cool. And I guess, I like to take opportunities to kind of show things that I think are representative of what math is like at higher levels. So, if you're someone who ends up going and taking like graduate level math classes, or even just sort of like upper level, past calculus kind of classes, you're going to start to see a lot more proofs. And, a lot of them can be really cool and really kind of use a lot of stuff that doesn't necessarily feel related to what you're doing. So I just wanted to take the opportunity to show you a proof that I think is kind of like that. So tomorrow we're going to be working with a similar rule called the quotient rule for taking derivatives of now when you're dividing two functions. And like I said, after that, we'll get into derivatives of trig functions. All right, thank you, and I will see you next time.